Right now, as you sit or lie down somewhere in the United States, maybe beneath the quiet glow of a bedside lamp in California, or in the humid midnight air of Florida, or in a small town stretching across the plains of Kansas, you feel perfectly still. The walls are not trembling, the floor is not shifting, your breath is slow, your body is calm. And yet, at this very moment, you are spinning through space at nearly 1,000 miles per hour because the Earth beneath you is rotating. At the same time, you are racing around the Sun at 67,000 miles per hour. The Sun itself is orbiting the center of the Milky Way galaxy at roughly 500,000 miles per hour. And that galaxy, our entire swirling island of stars, is also moving, tumbling through the expanding universe. You are not still. You have never been still. Nothing in the universe has ever truly been still. Everything is spinning. And tonight, as the world grows quiet, we are going to gently explore why. Before we begin drifting deeper into this cosmic rhythm, if this journey into the turning universe brings you even a moment of peace or wonder, consider softly tapping the like button and subscribing. It helps this channel continue creating calm, thoughtful science stories for curious minds. And I would love to know, from which part of the country are you listening tonight? Are you on the East Coast watching the Atlantic tides rise? In the mountains of Colorado? In the deserts of Arizona? Leave a comment and tell me where you are. It amazes me how far these quiet stories travel. Now, let us begin at the beginning, not with Earth, not with the Sun, but with the birth of everything. About 13.8 billion years ago, the universe emerged from an event we call the Big Bang. It was not an explosion in space, but an expansion of space itself. In the earliest fraction of a second, the universe expanded faster than the speed of light in a period known as cosmic inflation. Temperatures were unimaginably high. Energy and matter were indistinguishable. Quantum fluctuations, tiny ripples in the fabric of reality, were stretched across the newborn cosmos, and within those ripples lay the seeds of all future structure. At first glance, the early universe appears remarkably uniform. Measurements of the cosmic microwave background radiation, the faint afterglow of the Big Bang, show that matter was distributed almost evenly. But almost is the key word. Tiny differences in density existed, perhaps only 1 part in 100,000. In some regions there was slightly more matter, in others slightly less. Gravity, the quiet architect of the cosmos, began working immediately. Regions with a little extra mass exerted slightly stronger gravitational pull, drawing in surrounding matter. Over millions of years, those denser regions grew denser still. But here is where spinning enters the story. Imagine 2 clouds of gas drifting toward each other in the early universe. They are not perfectly aligned. One approaches slightly off-center. When they begin to collapse together under gravity, that slight asymmetry causes rotation. This is a fundamental principle of physics. When matter collapses inward unevenly, angular momentum arises. Angular momentum is the quantity that describes rotational motion, how much an object is spinning and how difficult it is to stop that spin. In everyday life, you can see angular momentum when a figure skater pulls in their arms and spins faster. As their mass moves closer to the center of rotation, their rotational speed increases to conserve angular momentum. The same law applies to collapsing clouds of gas in space. As a vast cloud of hydrogen contracts under its own gravity, any tiny initial rotation becomes amplified. The cloud spins faster and faster as it shrinks. Eventually, it flattens into a rotating disk. At the center, a star ignites. Around it, planets form from the remaining spinning material. This is how our solar system was born. About 4.6 billion years ago, a giant molecular cloud, a cold region filled with hydrogen gas and dust, began to collapse. Perhaps a nearby supernova shockwave triggered it. As gravity pulled the material inward, the cloud spun faster. It flattened into what we call the protoplanetary disk. At the center, pressure and temperature rose until nuclear fusion ignited, and the sun began shining. Within the spinning disk, particles collided and stuck together, forming planetesimals. These grew into protoplanets, and eventually into the familiar worlds we know: Mercury, Venus, Earth, Mars, and the gas giants beyond. Every one of those planets inherited spin from the original rotating cloud. That is why Earth rotates. That is why Jupiter spins even faster, completing a rotation in less than 10 hours. The spin was not added later. It was present from the beginning. A cosmic inheritance passed down from a collapsing cloud of gas shaped by the laws of physics. But why did the original cloud spin at all? To answer that, we must look even further back. The early universe was not perfectly symmetrical. Quantum fluctuations, tiny random variations in energy, were stretched during inflation. These fluctuations led to uneven gravitational fields. As matter moved under gravity, perfect straight-line motion was almost impossible. Any slight sideways motion became magnified over time. When matter gathered, it rarely fell straight inward. Instead, it curved, twisted, and began to rotate. In physics, if a system has even a tiny amount of angular momentum, and there is no external torque to remove it, that angular momentum must be conserved. This is the law of conservation of angular momentum. It is as fundamental as the conservation of energy. The universe does not simply erase or preserves it, and so once spin began, it continued. Stars spin, planets spin, asteroids tumble, galaxies rotate in vast spirals. Even black holes, the most extreme objects in the universe, can spin so rapidly that they drag space-time itself around with them, a phenomenon predicted by Einstein's general theory of relativity known as frame dragging. The twisting of space and time near a rotating black hole can be so intense that it alters the paths of nearby matter and light. But before we drift that far into space-time, let us return to Earth for a moment. The Earth completes one rotation every 24 hours. This rotation defines our day and night cycle. But it was not always 24 hours. Early in Earth's history, days were shorter, perhaps only 6 to 8 hours long. The reason is that Earth is gradually slowing down. The gravitational interaction between Earth and the Moon creates tidal friction. As ocean tides rise and fall, they dissipate energy. Over millions of years, this has transferred angular momentum from Earth's rotation to the Moon's orbit, causing the Moon to slowly drift farther away while Earth's spin slows slightly. This means that the rhythm of day and night has been gently changing for billions of years. Dinosaurs lived under shorter days than we do, and in the distant future, Earth's rotation will continue to slow, though the process is extraordinarily gradual. Yet even as Earth slows, it will not stop abruptly. Angular momentum resists sudden change. To stop Earth's rotation entirely would require an immense external force, something far beyond any natural process currently at work. Now let us widen our view again. Our galaxy, the Milky Way, is a rotating spiral of roughly 100 billion stars. If you could step outside it and observe from above, you would see vast spiral arms curving gracefully outward. The entire galaxy rotates around its central supermassive black hole, completing one full turn roughly every 225 to 250 million years. Since the time of the dinosaurs, our solar system has completed only about one orbit around the galactic center. The rotation of galaxies presents one of the most intriguing mysteries in modern astrophysics. When astronomers measure how fast stars orbit within galaxies, they find something surprising. Stars far from the center orbit faster than expected. According to visible matter alone, outer stars should move more slowly. Instead, galaxies rotate in a way that suggests there is far more mass present than we can see. This unseen mass is what we call dark matter. It forms a vast, invisible halo around galaxies, influencing their rotation and structure. So spin not only shapes galaxies, it reveals hidden aspects of the universe itself. Even on the smallest scales, rotation appears. Electrons possess an intrinsic property called spin. It is not spinning in the classical sense like a tiny ball, but it carries angular momentum as a fundamental quantum characteristic. This property influences magnetism, atomic structure, and the behavior of matter. Without quantum spin, chemistry as we know it would not exist. The stability of atoms depends on the quantum mechanical rules governing these tiny units of angular momentum. From atoms to galaxies, rotation is woven into reality. But perhaps the most soothing realization of all is this spin is not chaotic, it is ordered. It is predictable. It follows laws that are consistent across billions of light years. The same conservation principle that governs a spinning ice skater governs a collapsing nebula. The same equations that describe Earth's rotation describe the rotation of distant stars. And yet, despite all this motion, we feel still. We feel still because motion is relative. There is no universal reference frame that defines absolute rest. When you sit quietly in your home, you share Earth's rotation. You share its orbit. Everything around you is moving together. Without an external reference, motion becomes invisible. Stillness is an illusion created by shared movement. In Einstein's theory of relativity, there is no preferred state of rest. The laws of physics are the same whether you are standing on Earth or drifting in deep space. Motion only has meaning relative to something else. And since we are carried along by Earth's rotation smoothly and continuously, we experience calm instead of chaos. Tonight, as you rest, You are participating in a cosmic dance that began nearly 14 billion years ago. The spin of Earth traces back to a rotating disk of gas. That disk traces back to a collapsing cloud. That cloud traces back to primordial fluctuations in the early universe, and those fluctuations trace back to quantum processes at the dawn of time. Everything is connected by motion. The slow turning of Earth beneath your feet, the quiet orbit of the moon, the sun carrying us around the galaxy drifting among others in the local group moving within the larger cosmic web, layer upon layer of rotation, nested like the gears of an infinite clock. Imagine the sensation of gentle turning, not dizzying, not abrupt, but steady and ancient, the kind of turning that has no beginning in your memory and no sharp edge in your awareness. The Earth beneath you continues its rotation without effort. The air does not swirl violently. The oceans do not spill into the sky. Everything moves together in quiet agreement. And in that shared motion there is stability. Tonight, in this second chapter, we drift deeper into that stability and explore how spin shapes not only planets and galaxies, but stars, black holes, and even space-time itself. When a star is born, it begins as a rotating cloud of gas, just as we described before. But once nuclear fusion ignites in its core, something remarkable happens. The outward pressure from fusion balances the inward pull of gravity. This equilibrium creates stability. Yet the star continues to spin. Our sun rotates once approximately every 27 days at its equator, though interestingly, it does not rotate as a solid object. The sun is made of plasma, a hot ionized gas, and different latitudes rotate at different speeds. The equator spins faster than the poles. This is called differential rotation, and it plays a crucial role in generating the sun's magnetic field. Magnetic fields themselves are intimately connected to rotation. When charged particles move, they create magnetic fields. In a rotating star, vast flows of charged plasma twist and churn. The rotation amplifies magnetic activity through what physicists call a dynamo mechanism. This magnetic activity leads to sunspots, solar flares, and coronal mass ejections, eruptions of energy that travel across space and sometimes interact with Earth's magnetosphere, creating auroras that shimmer in green and violet curtains near the poles. So rotation does not merely keep stars turning, it powers their magnetic personalities. Some stars spin much faster than our sun. Young stars especially can rotate at extraordinary speeds. In certain cases, stars spin so rapidly that they bulge outward at the equator. The centrifugal force from their rotation partially counteracts gravity, stretching them into oblate shapes. If they were to spin just a little faster, they might begin shedding material into space. There is a limit known as the breakup velocity, beyond which a star would tear itself apart. The same principle applies to neutron stars, the incredibly dense remnants of massive stars that have exploded as supernovae. When a large star collapses at the end of its life, its core compresses dramatically. Conservation of angular momentum dictates that as the core shrinks, its rotation speeds up. Just as a spinning skater accelerates when pulling in their arms, a neutron star only about 20 kilometers wide can spin several times per second. Some neutron stars, known as pulsars, rotate hundreds of times per second, emitting beams of radiation like cosmic lighthouses. Each pulse we detect from Earth marks one complete rotation. Imagine that a city-sized object spinning faster than a kitchen blender, yet governed by the same conservation laws that apply to a child's toy top. And then there are black holes. When massive stars collapse beyond the neutron star stage, they form black holes, regions of space-time so intensely curved that not even light can escape. Many black holes spin, in fact most likely spin rapidly, because they inherit angular momentum from their progenitor stars. A rotating black hole is described by what physicists call the Kerr solution to Einstein's equations. Around such a black hole lies a region called the ergosphere, where space-time itself is dragged along by the rotation. This effect, frame dragging, means that nothing inside the ergosphere can remain stationary relative to distant observers. Space and time are literally twisted. Frame dragging is not limited to black holes. Even Earth, modest in mass compared to cosmic giants, slightly drags spacetime around as it rotates. This effect was measured by NASA's Gravity Probe B mission, confirming Einstein's prediction with remarkable precision. The twisting is minuscule, but it is real. The very geometry of spacetime responds to spin. Pause for a moment and consider that. The act of rotating does not simply move matter. It influences the structure of reality itself. Rotation also governs the architecture of galaxies earlier. We touched on how galaxies rotate and how dark matter plays a role. Let us explore that more gently now. When a galaxy forms, it begins as a vast cloud of gas and dark matter collapsing under gravity. As with stars and solar systems, any slight initial angular momentum becomes amplified during collapse. The forming galaxy flattens into a disk and begins to rotate. Within that rotating disk, density waves move outward, compressing gas into spiral arms. These arms are not rigid structures like the blades of a fan. Instead, they are regions of higher density moving through the disk, triggering bursts of star formation as gas clouds are compressed. The spiral pattern persists because of the galaxy's rotation combined with gravitational interactions among stars and dark matter. If galaxies did not rotate, their structures would look profoundly different. The elegant spiral arms that inspire artists and astronomers alike would not exist. Instead, matter might collapse more directly toward the center, forming a more chaotic distribution. Rotation creates order from collapse. Now let us turn our attention to a quieter but equally profound question: does the universe itself spin? This is not an easy question to answer. According to the cosmological principle, on very large scales, the universe appears isotropic and homogeneous, meaning it looks roughly the same in all directions. Observations of the cosmic microwave background radiation support this idea. If the universe had a significant global rotation, we might expect to see asymmetries in that background radiation. So far, measurements suggest that if the universe does rotate as a whole, it does so extremely slowly, if at all. The prevailing model, known as the lambda CDM model, assumes no overall rotation. Yet theoretical solutions to Einstein's equations do allow for rotating universes. One famous example is the Gödel universe, proposed by mathematician Kurt Gödel in 1949. In his solution, the universe rotates and permits the possibility of closed time-like curves, theoretical paths that could allow time travel to the past. However, our observable universe does not appear to match Gödel's rotating model. Still, the fact that such a solution exists reminds us that rotation is deeply embedded in the mathematics of spacetime. Even if the universe does not rotate globally, rotation emerges everywhere locally. It arises naturally from gravitational collapse, from asymmetry, from the conservation laws that govern physical interactions. But what if, just for a moment, everything stopped spinning? Imagine Earth ceasing its rotation instantly. The consequences would be catastrophic. The atmosphere and oceans would continue moving eastward at thousands of miles per hour, creating unimaginable winds and tidal waves. The redistribution of mass would alter Earth's shape, and the day-night cycle would vanish. One side of the planet would face perpetual daylight, heating dramatically, while the other would freeze in endless night. Yet such a sudden stop is physically implausible. Angular momentum cannot simply disappear. To halt Earth's rotation would require a torque so immense that it would likely destroy the planet. On a larger scale, if galaxies stopped rotating, their structural balance would collapse. Stars would move differently within gravitational potentials. Orbital stability would be disrupted. Rotation is not decorative, it is essential. Even on atomic scales, if quantum spin did not exist, the Pauli exclusion principle, which prevents electrons from occupying identical quantum states, would fail. Matter would behave entirely differently. Atoms might collapse. Chemistry would unravel. The stability of solid objects, including the bed or chair supporting you right now, depends on quantum mechanical properties linked to spin. So spin is not an accident. It is a foundational feature of existence. Yet there is something comforting about this. The same law that keeps galaxies turning also keeps your gyroscope balanced, your bicycle upright, your spinning coin wobbling before it falls. Physics is consistent. The universe is not improvising randomly. It is unfolding according to principles that are elegant and deeply interconnected. As you continue listening, imagine the layers of rotation again, but now with greater depth. Beneath Earth's crust, the molten outer core flows and circulates, driven partly by rotational forces. That motion generates Earth's magnetic field, shielding us from harmful solar radiation. Above you, the moon rotates as it orbits Earth, locked in synchronous rotation so that we always see the same face. Beyond, Jupiter spins so rapidly that it flattens visibly at its poles. Saturn's rings orbit in delicate balance, each particle following gravitational pathways shaped by rotation. Further still, stars orbit within globular clusters. Galaxies interact, sometimes merging their spins, combining in complex gravitational dances. On the largest scales, galaxy clusters move along filaments of the cosmic web, tracing patterns established by primordial fluctuations. The universe resembles a vast choreography. And yet, for all this motion, there is no central stage, no absolute axis around which everything turns. Each system has its own axis, its own rhythm. Rotation is local, contextual, relational. Einstein taught us that motion is relative. There is no fixed cosmic backdrop marking true rest. If you were drifting in deep intergalactic space, far from stars and galaxies, you might feel weightless and still. But even there, you would be moving relative to distant galaxies carried along by cosmic expansion. Stillness is always relative. Perhaps that is part of why we find comfort in contemplating spin. It reminds us that stability does not require immobility. The Earth is stable because it rotates consistently. The solar system is stable because planets orbit predictably. Motion, when governed by law, becomes harmony rather than chaos. As this second chapter gently winds down, imagine yourself not as separate from this motion, but as an expression of it. The atoms in your body were forged in ancient stars that spun long before Earth existed. The angular momentum that shaped those stars traces back to the earliest fluctuations of the cosmos. You are made of spinning particles within a spinning planet within a spinning galaxy. And yet you feel calm. Perhaps peace is not the absence of motion, but alignment with it, not because the universe has stopped spinning. It has not, but because your awareness of it has grown gentler. You no longer need the urgency of understanding. You can simply observe. The Earth continues its quiet rotation beneath you. Somewhere across the country, night is deepening. Somewhere else, dawn is beginning. The planet turns without sound. But nothing spins forever in exactly the same way. Rotation, like all physical motion, is shaped by time. And time carries with it a subtle direction, the direction of increasing entropy. Entropy is often described as disorder, but more precisely, it is the measure of how energy spreads out. Over long stretches of time, energy differences even out. Systems move toward balance. So what happens to spin in a universe that is aging? Let us begin close to home. The Earth is slowing down, very gradually. About 1.7 milliseconds per century are added to the length of a day due to tidal interactions with the Moon. It is a tiny change, imperceptible in a human lifetime, but relentless. Billions of years ago, days were much shorter. Billions of years from now, they will be longer still. The Moon, in exchange, drifts away from Earth at about 3.8 centimeters per year. This quiet exchange of angular momentum continues night after night, tide after tide. Eventually, far in the future, Earth may become tidally locked with the Moon, always showing the same face to it. The turning will not stop, but it will synchronize. This phenomenon is common in the universe. Our Moon is already tidally locked to Earth. Mercury is locked in a resonance with the Sun. Many exoplanets orbiting distant stars are likely tidally locked as well, one side forever facing daylight, the other permanent night. Rotation evolves. Even stars change their spin. Young stars rotate rapidly. Over time, stellar winds, streams of charged particles flowing outward, carry away angular momentum. The star gradually slows. Our Sun spins more slowly today than it did in its youth. When it eventually becomes a red giant billions of years from now, its outer layers will expand dramatically. As it expands, conservation of angular momentum will cause its surface rotation to slow further, like a spinning skater extending their arms outward. Then there are neutron stars, those dense remnants of exploded suns. They spin extraordinarily fast at birth, but even pulsars lose energy over time, radiating it away as beams of electromagnetic radiation. Slowly, steadily, they too spin down. Nothing in the universe escapes time. On galactic scales, rotation continues for hundreds of millions of years per orbit. But galaxies also evolve, they collide, they merge. When the Milky Way eventually merges with the Andromeda Galaxy in about 4 billion years, their spins will interact in a complex gravitational ballet. The two spiral galaxies will likely form a single elliptical galaxy. The ordered spiral arms will fade. Rotation will not vanish, but it will redistribute, becoming less structured. Zoom out even further to galaxy clusters, enormous assemblies of hundreds or thousands of galaxies bound together by gravity. These clusters also exhibit motion, though less organized rotation and more dynamic interactions. Over trillions of years, as the universe continues expanding at an accelerating rate due to dark energy, distant galaxies will drift farther apart. The large-scale cosmic web will stretch thinner. Will spin survive this expansion? Yes, locally. Even as the universe expands, gravitationally bound systems remain intact. Solar systems, galaxies, clusters. These structures resist expansion because their internal gravity is strong enough to hold them together. Their rotation continues within their local regions. But over unimaginable timescales, stars will exhaust their nuclear fuel, stellar formation will slow and eventually cease. The era of bright starlight will give way to a darker epoch. In tens of trillions of years, the last stars may fade. What remains will be stellar remnants, white dwarfs, neutron stars, black holes. These objects will still carry angular momentum. Black holes, in particular, may continue spinning for astonishing durations. Yet even they are not eternal. According to Stephen Hawking's theoretical work, black holes slowly lose mass through a quantum process known as Hawking radiation. Over timescales vastly longer than the current age of the universe, black holes will evaporate. As they lose mass, their rotation will also diminish. Spin, like all organized motion, gradually disperses. In the far future, a future trillions upon trillions of years away, the universe may approach what physicists call heat death. In this state, energy is evenly distributed. There are no significant temperature differences left to drive processes. Motion does not entirely cease, but it becomes random, unstructured. The grand rotations of galaxies will be gone. The bright turning disks of stars will no longer shine. The universe will still contain particles. Quantum fluctuations will still occur. But the large-scale choreography of spinning worlds and glowing spirals may fade into quiet uniformity. And yet even this is not certain. Physics continues to evolve. Our understanding deepens. There may be processes we have yet to discover that reshape this distant fate. For now, what matters is this rotation is not permanent, but it is persistent. It defines eras. It shapes structure. It allows complexity to emerge. Think of how different reality would be without spin. No days and nights, no seasons shaped by axial tilt, no stable planetary climates, no spiral galaxies forming new stars in their arms, no magnetic fields shielding atmospheres from radiation, no quantum spin structuring atoms. Spin makes habitability possible. It makes chemistry stable. It allows stars to form disks where planets can coalesce. It creates cycles, and cycles create rhythm. And rhythm creates life. Your own body follows cycles rooted in planetary rotation. Circadian rhythms, biological clocks, are tuned to Earth's turning. The alternation of light and darkness regulates hormones, sleep patterns, metabolism. Even your heartbeat echoes a repetitive motion, a pulsing rotation of blood through vessels shaped by evolutionary adaptation to gravity and motion. You are a creature of spin living on a spinning world in a spinning galaxy. As we come to the end of this journey, let that thought settle gently. Everything in the universe is spinning not because of chaos, but because of conservation. Because once motion begins, it continues unless acted upon. Because asymmetry at the dawn of time gave rise to rotation. Because gravity amplifies the slightest sideways drift into grand spirals of stars. And through it all, the laws remain consistent. The same angular momentum that governs a child's spinning top governs a neutron star rotating hundreds of times per second. The same relativity that predicts frame dragging around black holes explains the subtle twisting near Earth. The same cosmic expansion that stretches galaxies outward leaves local rotations intact. There is elegance in that continuity. If you imagine the universe as a vast symphony, spin is its steady percussion, not loud, not demanding attention, but constant. Every orbit, every axial turn, every galactic revolution is a beat in that cosmic rhythm. And tonight, as you rest, you are carried within it. The Earth will complete another rotation before you wake. The Sun will move slightly along its path around the Milky Way. The galaxy itself will drift imperceptibly relative to its neighbors. None of it requires your effort. None of it asks for your attention. It simply continues. Perhaps that is the most peaceful realization of all. The universe does not depend on our awareness to sustain its motion. The spinning began long before us. It will continue long after us. And in this brief human lifetime, we have the extraordinary privilege of understanding it, of tracing our origins back to rotating clouds of hydrogen and forward to galaxies turning in the dark. So as this story closes, allow your thoughts to slow even if the universe does not. Let your breathing find its own gentle rhythm. Feel the steadiness beneath you, not stillness, but stable motion shared by everything around you. You are not standing on solid ground in a silent void. You are riding a planet that spins with ancient patience. You are orbiting a star that circles a galactic center. You are part of a cosmos that has been turning since time began. And in that endless, quiet rotation there is something deeply comforting. The universe is moving, and you are safely carried within its turn.